By the way, maybe you've noticed, in the old movies, when it's time to zap the monster on the table and bring it to life, they always use lightning. I mean, always. And why? Well, because lightning is electrical, it turns things on, though exactly what lightning does is left to your imagination. Because, in the end, what makes life, that's still a mystery. But interestingly, and I didn't know this, it turns out that what makes lightning is also still a mystery. In fact, it's kind of a big mystery. Here's correspondent Chad Cohen.
It's an elemental force of nature, and still one of the most mysterious.
Lightning is very difficult to study. I think we probably understand better how a star explodes halfway across the galaxy than how lightning propagates from 6 miles up.
Lightning strikes the Earth 4 million times a day, and after hundreds of years of scientific scrutiny, we still do not understand the essential secret of how it begins inside a storm.
It's thinning out.
That's why Professors Ken Eck and Richard Sonnenfeld and their team from New Mexico Tech are on a 10,000-foot mountain waiting for lightning to strike.
We're trying to find something new about thunderstorms and lightning. That discovery, I think, is worth the risk.
Whatever causes lightning to start has always been hidden inside the clouds, so unlocking that process requires waiting for the weather to reach maximum force, then launching sensitive instruments into the heart of the storm. It's hazardous and frustrating.
Come on out. Go, go. Get going, get going. Hey, don't drop it. Don't drop it. Okay, let's go, let's go. Go ahead, you get in position. You get in position. Oh.
Let's go in, right, in. It hit the ground.
A thunderstorm has got the energy of an atomic bomb.
Dr. Martin Newman is the director of the International Center for Lightning Testing and Research in Camp Landing, Florida.
It's the brightest light that we see. It's the loudest noise that we hear. The only thing hotter than the lightning on Earth would be a nuclear weapon exploding.
But what triggers the release of all that power? We know that lightning is a huge electric spark, and sparks happen when positive and negative charges build up so much energy they leap through the air to get at each other. It can only happen when the negative charge in that ball on the right and the positive charge in that metal rod on the left get so overwhelmingly strong they cut a path through the air in the middle.
It's like a hose full of pressure and it can't hold on anymore.
That's what most scientists think is happening inside thunderstorms, as ice and water particles collide with each other, moving electric charges to opposite ends of a cloud. When the charge above and the charge below get strong enough, they leap through the air as a bolt of lightning. Except for one thing. When you actually examine the storm cloud, the strength of the positive and negative charges and the electric field around them isn't nearly enough to create that big spark.
Well, the problem is after decades and decades of measurements up in thunderstorms, nobody has ever managed to find an electric field anywhere near that big.
Dr. Joe Dwyer is a professor at Florida Tech.
Well, maybe we're looking for something that doesn't exist. Maybe there's something wrong with our understanding about how electrical discharges get started in places like thunderstorms.
So if thunderclouds, even great big thunderclouds, don't have electric fields big enough to generate the giant spark that lightning actually is, where's all that energy coming from? Well, here in Florida, they have a pretty dramatic way of trying to figure that out. They launch rockets with really long wires attached to try to create that express lane to ground that lightning likes so much.
To get lightning from these clouds to strike where scientists can measure it requires a simple trigger.
First of all, you need to have a propellant that can get this thing up there in a hurry. It has to be able to go 700 yards or so in about 2 seconds.
And what is this actually? This is it just copper wire?
It's Kevlar covered copper wire.
Kevlar, okay.
So we load it, connect it electrically. When we're about to fire, switches are turned on here manually. After that, everything is done with air pressure from downstairs.
Okay, Casey, tube 2 is armed. 3, 2, 1, fire.
From 2,000 feet up, the wire triggers lightning with a path to ground higher than the Empire State Building. And when it strikes, over 100 million volts zapped the array of test equipment on the ground.
Okay, tube 4 is good. Go ahead and fire 11 when ready.
Tube 11 is armed. 3, 2, 1, fire.
The rockets are, for the first time, allowing physicists to experiment with lightning under repeatable and controllable conditions, so that now Joe Dwyer and other researchers can test an alternate theory of how lightning starts. That theory is called runaway breakdown.
Using this model, the energy field inside the storm cloud, that force between positive and negative, too weak to form a bolt of lightning, is struck by outside particles, bursts of electrons, which carry their own energy, very high energy. And with that added energy, you can now get that big spark.
You'll end up with an avalanche of electrons moving near the speed of light. Now this model will work as long as you have one fast electron to start it off. Sort of the finger that pushes the first domino to get the whole thing started.
And here's where things get really interesting. Joe Dwyer and many other scientists believe that this outside energy force comes not from the clouds, or anywhere else on Earth for that matter, but from cosmic rays, tiny subatomic particles ejected from dying stars millions of years ago and billions of miles away. But how do you test this theory?
We have 10 of these detectors spread out over the facility right now.
Well, it turns out when cosmic particles hit the Earth's atmosphere, they leave a unique signature in the form of gamma and X-rays. If scientists can detect these X-rays, they'll have the proof they need.
This is what's called a sodium iodide detector. There's a piece of crystal in here that will absorb X-rays and gamma rays. I mean, these things are not difficult to measure.
That's where triggered lightning comes in. For the first time, the Florida Research Center's rockets allowed Dwyer to place his X-ray detectors in lightning's path.
Straight up.
He made his first series of measurements in 2002.
A big negative voltage pulse would mean we got a burst of X-rays in the detector. And so I actually didn't think we were going to see X-rays. The first plot we brought up, there was a nice little pulse that looked just like an X-ray right at the time that the lightning occurred. Now, that's interesting, you know. That's probably a coincidence, you know. What's the chance of that? So we looked at the next lightning stroke, and there was an even bigger pulse, and the next one, and the next one, and every one had these pulses that looked exactly like X-rays. I think I just about fell out of my chair at that point.
Every single lightning strike Dwyer measured showed the presence of X-rays. But ground measurements can't reach high enough to where lightning actually starts. For that, you need to get instruments right up into the heart of the storm.
We finally have the technology to build these instruments that are small enough and rugged enough to handle the thunderstorm environment.
Lightning is striking all around them. It's time to launch.
One event won't be enough. I mean, if we see an X-ray burst and we call it quits on one event, well, that's not good enough. And it's just going to take a lot of measurements to get in the right spot at the right time.
4, 3, 2, 1, go!
The balloon is sucked into the storm,
Yeah!
trailing its cargo of instruments. Launches like these have finally traced X-rays all the way up to where lightning begins, and have given scientists the strongest evidence yet that lightning's spark comes from forces outside the Earth itself.
These cosmic rays may be the link which will connect a dying star halfway across the galaxy with lightning.